Double replacement. Single replacement, one person replaced another in a couple, right? It was that cutting in at the dance. Okay. Double replacement, how many things are replacing? Two. How many things are being replaced? Two. What happens to the ones that are being replaced? They do the replacing. They replace each other. So in our dance analogy, it's square dancing. You got couples on the floor, swing your partner around and around, pick her up and throw her down. Out of man left, change partners. That's what you're doing is you're changing partners. Okay? In our dance analogy. So, two things replace each other. Why is this not running? Yeah, two things replace each other. They're going to switch partners. So I got two couples when I start. I have two couples when I end. They're just not the same couples. So that means I have to have couples when I start. That means I have to have compounds. So the reactants have to be compounds. And they're going to be ionic compounds or acids. You don't do this with molecular compounds or ionic compounds or acids because ionic compounds and acids have partners because they have charges. They have a positive charge and a negative charge, so they have a partner. Most often, this happens in aqueous solution. So, there's my reactants. Sodium hydroxide and iron 3 chloride. I recognize this as a double replacement reaction because NaOH is an ionic compound, FeCl3 is an ionic compound. I have two ionic compounds. Because we've already done one compound, two elements, an element in a compound. Now we're doing two compounds. Let me see, we're just working our way through. And what happens is it's all your point of view thing. I pick the positive ions as changing place. It's equally valid to say the negative ions change place. But I like to pick the one in front because it makes it easier to think about. So if the positive pieces are going to change place, sodium is the positive piece here, and it's next to hydroxide. Iron is the positive piece here, and it's next to chloride. So the sodium is going to end up next to chloride, and the iron is going to end up next to hydroxide. So they change partners. Fe3 plus ends up next to the OH minus. I had to figure out the charge of Fe on the other side. I knew Fe was 3 plus because it was FeCl3. Whatever charge it has on this side, it's got it on that side. Okay? So the Fe ends up next to the OH, the Na ends up next to the Cl. Notice I did not bring the coefficient for Cl, or the subscript for Cl. Because how many they partner with is based on charges, not how many there were over there, but on what charge they have. So the formula for the iron 3 and hydroxide is not going to be FeOH, it's going to be FeOH3. And the sodium chloride is going to be NaCl. Okay. So I actually color-coded the other side so you can see that they switch partners. Yeah.
So it doesn't matter, like, Na is below Fe
Well,
or
actually, the activity series won't do us any good because there's always going to be one above and one below, but then there's always going to be one below and one above, right? Doesn't matter. We'll talk about why these happen a little bit later. So we're going to have a different way of predicting these because this is not about, it's not replacing it over and it's got no place to go. It's replacing it and it's got some place to hang on to. Okay, so they're just trading places And they always trade places. If it happens, they've traded places. If it doesn't happen, they haven't traded places. Okay, let's look at what we're talking. Oh, I had to balance it. I needed 3 NAs. And I need 3 OHs, so I put the 3 in front of NaOH, which gave me 3 NAs, which means I need 3 NaCls, which gave me 3 Cls, which I needed for my iron 3 chloride. So there's a picture of my reactants. 3 sodium hydroxides, 1 iron 3 chloride. And what do they do? Atom and lift, change partners. Okay. Makes sense? So the sodium's with the hydroxide, the iron was with the chlorines. Turns into the irons with the hydroxides, and the sodium's with the chlorines. Okay, since they're changing partners, another way of looking at this is they're changing names. It was sodium hydroxide and iron 3 chloride. On the other side, it's got to be iron 3 chloride, or iron 3 hydroxide, and sodium chloride. All they did was change names. Right? Just change the last name and then write that formula. That's another way of looking at it. Since the name is just the ions. Make sense? Okay, let's do a few. Right, for right now, we're going to assume all the reactions take place. So, CaCl2 plus NaOH. So they're going to change partners. So the Ca is going to switch with the Na. So the Ca is not going to be next to Cl, the Ca is going to be next to OH. And the Na is not going to be next to OH, it's going to be next to Cl. Notice I did not bring the subscript over. The subscript's about charge. Okay? Cl is 1 minus, Na is 1 plus. That's the right formula for NaCl. OH is 1 minus, Ca is 2 plus. That's not the right formula. Do the crisscross, so it's got to be CaOH2. So calcium chloride and sodium hydroxide make calcium hydroxide and sodium chloride. Just change the names. And I got to balance it. 2 Cl, so I put a 2 in front of NaCl, which gives me 2 NAs. So I put a 2 in front of NaOH, put a 2 in front of OH. If you write these charges wrong on this side, if you write the wrong formulas, it will never balance. So if you keep going and keep changing the numbers over and over again, that means you've got a wrong formula in these someplace. That's going to be your clue that your formula's wrong, is it won't balance. Unless you leave everything as ones, which it would balance, but you should have caught that one too. Make sense? So if it doesn't balance, check to make sure you got those subscripts right. Next example. Pb NO3 2 plus Ki. What's it going to make? Well, the PV and the K are going to switch places. So the PB is going to be next to I, and the K is going to be next to NO3. I keep the 3 from NO3 because that's the piece. I don't keep the 2 on the outside because that's how many of those pieces. So I keep the 3 but not the 2. My piece is nitrate. I had 2 of them on the reactant side. My piece is still nitrate on the product side. Now I got to do charges. Notice this is the same thing. Do what the name says. Do charges to figure out the formulas. PB, I got to get PB from this side. So nitrate was 1 minus, so that's 2 negatives. So that's 2 positive. The PB had to be 2 plus here. So it's got to be 2 plus here. So that means it's got to be PBI 2. And then I have to balance it. 1 PB, 2 NO3s. So I'm going to put a 2 in front of KNO3. 2 Ks, put a 2 there, gives me 2 Is, and it balances. These will balance easy, one element at a time, and you'll end up balanced if you've got the right subscripts. Make sense? So, we just did that. Actually, that was not worth doing because we just said, let's do this one. Phosphoric acid and calcium hydroxide. The Ca and the H are going to change partners. The H was next to PO4. It's now going to be next to OH. Hey, that looks familiar. And the Ca is going to be next to PO4. Ca is 2 plus, PO4 is 3 minus. So that's Ca3, PO4 2. H is 1 plus, OH is 1 minus. That's the right formula for water. Okay. So we can use that trick again. I have to make water. I have to make hydrogen hydroxide. So I have to have equal amounts of hydrogen and hydroxide. On the other side, it's 3 hydrogens and 2 hydroxides. Where are they going to run into each other? At 6. Right? So I know this has to be a 6. Which would mean that I would need 2 of the phosphoric acids. That would give me 2 phosphates, which I wanted anyway. And I'll need 3 of the calcium hydroxides, which will give me 3 calciums, which I wanted anyway. So we're balanced. 6 hydrogens, 2 phosphates, 3 calciums, 3 calciums, 6 hydroxides, 6 hydroxides. Hey, this was an acid. Okay? All the things with hydroxides are bases. What happens when you mix an acid and a base? You get water. You have neutralized the acid and the base. Acid and bases are not opposite, they just react with each other to make water and cancel each other out. The hydrogen ion and the hydroxide ion make water. That's what makes it neutral. So, how do we know if these are going to happen? We can't use the activity series. It won't do us any good. Because there's always be one below and one above, which means there's always one above and one below. There are 3 conditions that will make it happen. 1, it doesn't dissolve in water and forms a solid. So remember, most of these happen in aqueous solution. So if they happen in aqueous solution and it forms a solid, that solid will separate and sink down to the bottom. These are the ones that we could put the down arrow for. Ones that would settle down to the bottom. To show you that, a few seconds ago, we wrote an equation for what would happen if you mix lead nitrate, clear solution of lead nitrate. So this is lead nitrate dissolved in water. And that's potassium iodide. Nice clear solution. So I pour it in. it's cloudy, you can't see through it. That means there's a solid there, blocking light. Okay? If I let this sit over time, the yellow stuff will sink down to the bottom. Because it's a solid in liquid, it's going to sink down. So this reaction happened. How do I know? Because I see the solid. Okay? Second reason it would happen is it forms a gas that bubbles out. Or it's a covalent compound, usually water. Then if it's covalent, then it's molecular. Molecular means it doesn't have ions anymore. You got rid of the ions by making something molecular. It says usually water. It's always water. Okay? That's why the acid-base reaction we just saw happens, because it made water. And water hangs onto itself. So I no longer have the calcium hydroxide or the phosphoric acid, because I've taken the hydrogen and hydroxide away from them. They're stuck in the water now, because water sticks together. And that's what these are all about. These are ways that they separate from the solution. That they stop being ions, because we said that when I put that lead nitrate in, it was ions, right? Ionic compounds fall apart as ions. So there's a whole bunch of ions. When it's a solid, it's no longer individual ions. When it's a molecular compound like water, it's no longer individual ions. And when it's a gas that bubbles out, it's gone there. There aren't ions there because they're no longer in the container. Right? It's about removing them from that solution. That's what these three things are about. What could happen that could take the ions out of solution? Okay. And polyatomic ions don't change from one side to the other. So if it was nitrate on one side, it's going to be nitrate on the other side. So hydroxide on one side, it'll be hydroxide on the other. We'll talk more about this tomorrow. And then we'll start predicting, we'll write the equations and predict whether they're really going to happen tomorrow. That's more to learn about that. First, I want to get you to write the equations, then we'll start talking about whether they happen. Make sense? So, next problem. So for right now, assume they all happen. It says to tell me why they happen. We'll deal with that tomorrow. All right? It involves deciding whether things form solids. Oh, we got bad news for you. It's only one side. But you might need to do some scratch work along the way. That's pretty close together. So remember, the process is do what the name is. Don't worry about it. Then use charges to figure out what the real formulas are. Then